Know your PHY. What's the PHY? The physical layer. You need to know how a NIC works. Now, NICs are entirely different in wireless than wired. We think of a NIC as something that just convert ones and zeros on one side into some form of media and send them on the other side. But if you start down at the NIC layer with Wi-Fi, you'll realize that the radio tap header is something that the receiving NIC adds to the frame that comes in. Meaning, every single device receives a different radio tap header. They may have different spatial streams. They'll be in a physically different location. They have a different antenna. So even though an access point transmits a single frame payload that's identical, every client that hears it is going to hear it differently. That's a pretty big change in what we're doing. We need to understand RF media, how it works, the whole modulation encoding scheme, and what happens when you change from a 20 to a 40 to 80 megahertz wide channel. That's changing our network. And don't get suckered. I don't know a better word to say. Don't get suckered into thinking there's something magic about 80 megahertz wide channels. They're obviously 4 times better. No, they're not 4 times better. The things about the PHY, spatial streams, modulation, coding, and the entire contention process are what's going to drive your design. Co-channel interference, Wi-Fi 802.11 is 100 times more sensitive to other Wi-Fi than to non-Wi-Fi. It's built right into the protocol. So don't ignore the parts that Wi-Fi is the #1 enemy of other Wi-Fi. It's going to have to come into your design process. You need to also understand how a single frame is transmitted. Because if you don't, it's going to come back and bite you. In this picture, the only thing that crosses the wireless to wired boundary is the little teeny blue sliver. All the other parts take time. And again, in Wi-Fi, the thing we have least of is spectrum. And so if we can take the air time that's being used and make it more efficient, we can get more data to go over the same network. So if we want to solve for capacity, more devices attached in the same area, what we're really solving for is speed. If we can deliver faster data, we can make each user use less air time. And if they use less air time, more users can use it. So capacity is about speed. It's not about adding more APs. Yeah, AP salesmen would love you to know that, but that's not really what it's about. There is a chunk of time, in this example, about 38% of our time is just wasted in arbitration. That's because the protocol that runs under Wi-Fi uses this distributed coordinated function. Now, just if you take those words apart, you go, what? We're coordinated, but we're not. We're distributing coordination. Yeah, what we're doing is we made up a system that didn't require things to talk to each other in order to work. And it does it by using a whole lot of time to get there. There's a whole lot of overhead for RCS, CTS, and then we have our little teeny payload. And in front of the payload is some more overhead, 802.11 overhead. And then we have a CIF-SAC at the end to get a little block act that comes in. Out of all the time we spend in the air, a very small portion of it is actually going across the wired boundary. All the rest of the colors, other than blue, they're in the air, but they're not on the wire. Again, if you understand this, you'll also understand why it's really tough to get to a position where you need MGig to support APs. Now, you might want to use MGig. Nothing wrong with MGig. I like MGig. Please. But that's not the reason you don't go to MGig isn't because Wi-Fi demands it. It's just not showing up. Let's show another example now of the differences when we're looking at two different things. The first one up is going to be 20 versus 80 megahertz channels. And the second is what happens when we take the best possible Wi-Fi and compare it to the worst possible Wi-Fi. First up is 20 versus 80. The airtime, the contention to get the airtime, exactly the same for both of them. RTS, CTS, exactly the same for both of them. And in this color scheme, this is using a different tool. Green is the payload. And you can see as we went from a 20 megahertz to 80 megahertz, yeah, the payload went faster. All the other pieces didn't. So the actual net savings in time is very small. And I'm not even showing here, the downside of going to 80 megahertz channels is you're going to lose 6 dB of SNR. Additionally, you're going to have a whole lot of the primary channel versus secondary channel, and the OBSs overlap, all sorts of other things for this little teeny gain. Now, your end users, when they go to an 80 megahertz channel, they'll see this bigger number, but that number is only for the payload. We really need to be looking about the entire airtime. Now, the bottom of this slide, also very important, the bottom of this slide is showing what if we took a very poorly run Wi-Fi network. It was designed with only 6 meg for the management frames. 24 meg is the max we'll allow to go through for the data rate. We're not going to allow it to float faster. We're going to lock it only at 24. 20 megahertz wide channel, single spatial stream, MCS of only 3. That's a really poorly performing Wi-Fi. And then we're going to compare it to someplace where we put the control management frames at 24 meg. We allowed it to float all the way up to full MCS 9, 2 spatial streams, and you go, yeah, it's faster. Really? Not that much faster. The overhead is still there. Yeah, the control frames went a little faster and it took a little less time. But it's not 4x, 5x different. It's less than 1x differential between the fastest and the slowest Wi-Fi. Again, it's all about airtime. And the reason rule number 1 is know the PHY is because that's where all these little things happen. Another thing that happens in your PHY is how does a client join? There's an entire process of how a client goes through association, probe request, probe response, authentication request, authentication response, association request, association response. And then the client can get on the network. And then at that point, there's either open, PSK, or .1x. That's the authentication portion. And then there's an encryption portion. And then we have port control. Then we hit the upper layers to get DHCP, DNS, VLANs, etc. Once you have all of that opened up and you can actually hit the LAN, then you hit the captive portal. So if you hit the captive portal, that means all of the 802.11 things are already working. A lot of our end users think the captive portal is the beginning. It's actually the end. So you should really understand how this whole flow works, and if you're troubleshooting where each of these things happen. I like to design with a open, no authentication, no encryption, no captive portal. Yeah, so I can prove it's not the Wi-Fi. Test your Wi-Fi separately and then add each of those other functions in that are on top of Wi-Fi. 802.11 is the blue 802.11 association. All the other things are on top. So design to make sure that works properly. The other pieces are actually more about other things, not the actual 802.11 itself.